So, während die Letzten ihre Plätze einnehmen, würde ich dann kurz den Marius anmoderieren. Der Marius ist ganz frisch am CISPA als PhD-Student vom Ben. Und wie wir alle wissen, wenn der Ben irgendwo seine Finger mit dem Spiel hat, dann geht es wahrscheinlich um Cross-Site-Scripting. Und so auch in dem Fall hier. Das, was der Marius uns heute vorstellt, ist als NDSS-Paper angenommen und published worden. Und Marius würde den Vortrag auf Englisch halten, weil auch die Slides in Englisch sind und weil es dann einfach im Video nachher für ein größeres Publikum auch verstehbar und erreichbar ist. Und damit würde ich euch bitten, alle mal den Marius zu begrüßen.
Yeah, so thanks for the introduction. Today I'll present to you joint work with my colleagues Martin from Braunschweig and also with Christian Rosso and Ben Stock, my supervisor from CISPA. And as you can already see at the title, and which was already hinted at, this talk will be focusing on cross-site scripting and a rather overlooked form of cross-site scripting, which we investigated in the wild and tried to exploit it at a large scale. And just to shortly recap what we know about cross-site scripting and what we typically talk about when we talk about cross-site scripting is we have these 4 dimensions among which we distribute the different kinds of cross-site scripting. So on the one hand side, we have where the vulnerable code resides, which is either the client side or the server side. And also we have whether or not this is like a one-shot vulnerability, which is typically referred to as reflected, or whether this vulnerability is actually triggered on each page visit, so rather a persistent version of that vulnerability. And as already stated, in this talk, I will be focusing on the persistent client-side version of cross-site scripting. And you can see a little code example which shows you a vulnerability. So in this case, there is an entry being stored in the local storage with the key name. And in this case, it's just taken whatever is after the hash mark in the URL. And later on, the same entry is being retrieved in a code executing context. In this case, it's document write. And an attacker could exploit this by just providing his URL where he has this attack payload behind the fragment. And you might wonder yourself, so persistent client-side cross-site scripting, we should know about this, right? This should be known by now. We should have large studies looking at this particular threat. And in fact, I've taken this quote from the OWASP wiki, and I'll just read it for you. So with the advent of HTML5 and other browser technologies, we can envision the attack payload being permanently stored in the victim's browser, such an HTML5 database, and never being sent to the server at all. And this is an excerpt from the stored cross-site scripting paragraph of the OWASP wiki. And this summarizes what we know about the threat of persistent client-side cross-site scripting. We have this idea that this could be exploited and this could be a threat, but we've never had any large-scale study which showcases the impact of this threat on the web as we know it. There were some papers back in 2010 which did some manual analysis of web applications and which found some cases where they could exploit persistent client-side cross-site scripting. But other than that, we don't have any knowledge about how this threat is actually present throughout modern web applications at a large scale. And to that end, we propose some research questions which we want to answer with our research, and which is also the outline for the rest of this talk. So at first, we wanted to investigate how many of the top sites are actually making use of some form of storage technology in their website code. And out of those, how many could actually have an exploitable flow which originates from a web storage to some code executing sink, which an attacker could potentially exploit. But the only presence of this flow doesn't mean that a website is vulnerable, because the attacker first needs to store his malicious payload somewhere in the user's browser. And to that end, we also looked at different attack vectors on how an attacker can achieve that, and we proposed two attacker models which can actually achieve this kind of storage of a malicious payload inside the user's browser. And to answer these questions, we built up on previous research, which was the taint chromium proposed by Likis et al. And we used this tainting engine, which was built into Chrome, to find these flows originating from storage and going into a code executing sink. But we needed to do a number of improvements, which I'll shortly cover when they appear in the talk. But let's just look at what technologies we actually can use on the client side in order to store data there. And the first thing which might come to your mind is obviously cookies. The thing with cookies is that they are typically used to store some session information or some preferences, like, for example, the language. And they're bound to the effective top-level domain +1. What this means in terms for an attacker is that you can, for example, set cookies from a subdomain to a parent domain, so for a parent domain actually, which comes in quite handy for an attacker later on, but we'll talk about that. What's the downside of cookies? That they're limited in size, so you can only store like 4096 bytes in there, and they're also limited in their character set. So if you think about an eval sync where an attacker wants to execute code, he might need to escape previous code, which the developer actually intended there to be, and he might need to use a semicolon to actually break out of previous code segments. And this makes exploitation of this threat much harder because you have only this limited character sets, which you cannot use any semicolons because they're actually used as a delimiter in the cookies. On the other hand side, with the advent of HTML5, we have something which is called web storage. So we have, on the one hand side, we have session storage, and on the other hand side, we have local storage. Session storage being only present for the current browsing window. So when you close your browsing window, actually every entry in the session storage is cleared and deleted. So it's not too much use of an attacker if he wants to have a persistent execution. So we discarded it for the rest of the analysis. On the other hand side, local storage is actually persistent throughout browsing sessions and also throughout windows. And also, in contrast to cookies, the web storage is actually bound to a specific origin. So, for example, foo.example.com has a different local storage than example.com. So an attacker would need to get his payload into the right origin where also a vulnerable flow originating from storage goes to an executable sink. And in the down right corner, you can again see the example which was previously hinted at. So the developer makes use of this get storage function inside the code executing context, in this case eval. And if the attacker manages to tamper with the database, he can just get his code executed. But I've already also hinted at the attacker models which we want to discuss. And for one attacker model, specifically the network attacker, we first need to talk a little bit about defense mechanisms which might be in place. So in this case, we'll just shortly recap Hsts for everyone to get on the same page. So Hsts is a response header which you can set, which you can send from your server, and it instructs the browser to only visit that site via HTTPS from this point onward, up to an expiry period. And what's important for Hsts is that you can make use of the include subdomains flag, which instructs the browser to also make use of this mechanism for each subdomain. So you can only serve the subdomains via HTTPS. This can, of course, be preloaded in the browser such that you don't have this first use problem. And we've also concerned the preload list in order to compile our list of sites which are vulnerable. But let's talk about the attacker models now. So the attacker wants to get his malicious payload somewhere in the browser of the victim. And the first attacker model which came to our mind was the network attacker. And the capabilities of the network attacker are as usual. So he can modify any unencrypted connections, but he cannot get his hands on any TLS certificate in order to tamper with encrypted traffic. So what this yields the attacker for capabilities in terms of tampering with storage is actually he can set cookies for domains which are not deploying HSTS, or for those domains which actually deploy HSTS, but do so without the include subdomains flag. So think about you're sitting in your local coffee shop and surfing the web, and you need to hit this, and you actually encounter a captive portal, and you're served an HTTP site. And this site could, for example, just frame or actually have a hidden iframe which points to a non-existing subdomain of the page where an attacker wants to attack, and just set a cookie for the parent domain. So in that case, an attacker could actually make use of the missing include subdomains flag in order to set a cookie for the site he wants to actually target. And in terms of local storage, he can obviously only set storage entries for the specific origin, so only for the HTTP version of the website. A second attacker model which we had in mind is, of course, the web attacker. The capabilities of the web attacker are, again, as usual. You can lure your victim on your website, or you can just get him some link where he clicks on. And the first attack vector which an attacker then can use is obviously an existing cross-site scripting in the same site in order to plant his payload. Or what he can also do is he can use an existing flow which, for example, originates from the URL and ends up in some storage. So you can envision that you you take what is written in the URL after the fragment, you paste it into some storage entry, and later on you retrieve the same storage entry and use it in a code executing sync. Of course, these kind of double flows, they are quite hard to actually exploit in the wild, because on the way from the URL to the storage entry, and then again from the storage entry to the sync, there are lots of string manipulations going on, and there's a lots of also maybe encoding going on, which makes automatic exploitation of this thread really hard, which is why we mostly focused on the first attack vector, namely that an attacker abuses an existing cross-site scripting flow. But you might now wonder yourself, okay, if we already have an existing cross-site scripting in the same site, what does an attacker actually gain with the persistent threat? And this is really a valid question. And if you think back, what you know about and what textbook cross-site scripting attacks always tell you is that the victim is lured onto a site, cross-site scripting happens, and the attacker just steals your session identifier. But by now, for modern web applications, this is no longer the case, because most of the session identifiers are, for example, protected via HTTP-only cookies, so they're not accessible via JavaScript. And also, if you, as a security-aware user, would be surfing in your local coffee shop, and suddenly you're being locked out of Facebook, and you're being tasked with logging in again in an unsafe environment, you might actually hesitate. And you might reconsider and doing so at a safe environment, so for example, when you're back home. And in that case, potential payloads which an attacker might want to execute persistently, for example, consider just like a keylogging JavaScript, which is executed on each page visit. So in that case, for example, you're again back at home, and your session of Facebook would normally expire, and you're tasked with logging in again. Everything is benign because you're at home and nothing bad could happen, and then you would enter your credentials. And in this case, the attacker would again get access to your session. On the other side, we can also, or an attacker could also make use of cryptojacking in order to monetize the user's resources. So whenever the user visits the web page, he could just run his crypto mining script in the background and just generate some constant cash flow for the attacker. But after having talked about all the methodology, let's talk about what we actually found in the wild. So what is the results which we got with our analysis? And this table is basically split into two parts. So on the one hand side, we have the cookie flows which we found. On the other hand side, we have the local storage flows. And we've also grouped them according to the different things which we considered. So on the one hand side, we have HTML executing things. So for example, inner HTML. We have JavaScript, so for example, new function or eval. And we've also had script source. So for the script source exploits, we considered an attacker controllable flow which determined from which hosts could scripts be fetched from. So in that case, for example, we found actually 1,385 flows which originated from cookies and ended up in some sort of script source, so where somewhere part of a URL where a script should be fetched from. And out of those, we found that around 533 are unencoded, so only in plain, so there was no string manipulation or encoding going on. And we could exploit only 17 of those for the case of script source. If you now look in contrast to the first column, so in this case HTML, we can see that around 27% of the flows which we found originating from cookies and going into a code executing sync were actually exploitable. And if we compare this to local storage, what we can see is that the percentage numbers of flows which are exploitable are way higher. And we attribute this to the fact that developers put their trust into the integrity of this web storage. So they think whatever is written in there actually originates from them. So they don't think that there is an attacker, or they're less likely to be an attacker who can tamper with these storages. And these are just the raw numbers of exploitable flows which we found. If you can see, we have the total number of flows. So we have like 213 cookie flows which we could exploit, and 222 local storage flows which we could exploit. And in total, we could exploit 418 sites. And if you pay close attention, this doesn't sum up, which just means that some sites had both a vulnerable cookie flow and a vulnerable local storage flow. But as already hinted at, this is if an attacker can just simply tamper any storage he likes. If we combine this information with our attacker models, we can actually see that around 290 sites can be exploited by a network attacker, either because the site did not make use of HTTPS at all, or because they lacked the include subdomains flag if it was a cookie flow. And if we look at those websites which had both a client-side reflected XSS and the persistent client-side XSS, we found actually 65 sites who had both of these, such that an attacker could craft an end-to-end exploit. And especially for the web attacker, these results have to be considered lower bounds, because we didn't try to have any means of code coverage, which would be tremendously hard in any case. And also, we did not try to perform any logins. Also, we only considered reflected client-side XSS. And also, what we have seen is that the Chrome usage statistics suggest that around 15% of the page hits actually make use of something called document domain, so domain relaxation, which would mean that if a subdomain relaxes its origin to the parent domain, and the parent domain does the same, that the subdomain could actually also interact with the storage of the parent domain. So in that case, we could even have more exploits going on if we have, for example, an XSS only in the sub-origin. What we also did not consider were any flows which originate from storage and go back into storage. So we found quite a lot of these, and it would be quite interesting to look if there is anything more going on there. But what we also actually wanted to do is to get a feel on what the developers try to achieve with their stored data on the client side, and to get a feel on how we could improve upon security by proposing appropriate means to fix these vulnerabilities. And on 214 domains, we found evidence that the developer wanted to just store some textual information in the storage mechanism. So this could be addressed with some proper encoding, or just using safe syncs. So instead of using inner HTML, just use inner text. On another 108 domains, we found evidence that they make use of some sort of structured data, so for example, JSON or stringified JavaScript objects. And guess what? The developer just made use of eval to parse JSON. And the only thing which you can propose is that just use JSON parse. It's working by now. On another side, we also looked at those sites who could just plainly use JSON parse, because for stringified JavaScript objects, you cannot make use of JSON parse. You actually need eval. And I think on 85 sites, if I'm not mistaken, you could just simply swap it out. And on the other sites, you would have at least to do the effort to substitute your stringified objects with real proper JSON. What we also found is that 100 domains tried to make use of some client-side caching. So they either stored HTML in there, or they stored some JavaScript code in there. And for that, there's actually, with the advent of the progressive web apps, this mechanism called Serviceworkers, which is specifically intended for this use case. So the service worker is actually running in a different JavaScript execution context, and also has its own means of storing persistent data, which is inaccessible from within the site, which means that this could be a proposed defense mechanism for such that you don't have to store your code, or you cache your code on the client side in your local storage, which could be tampered with. Another thing is that back in 2012, Martin proposed some integrity measurement for this storage, because back then they have already seen that people make use of client-side code caching, and this could also be a means which we could use or which we could actually use to improve upon this situation. On another 28 domains, we actually found that they performed some kind of client-side load balancing. There were actually some host names being stored in the respective storage mechanism. And so basically what they did is just consult the entry and look where they should fetch additional resources from. And for that, you can just simply refer to a whitelist of hosts you expect, and if something differs, you just refrain from loading any scripting resources from there. But now I'd actually like to show you one case where we had an end-to-end exploit on a Chinese single sign-on provider. And hopefully the video plays? Yeah, right. So in this case, we both used a reflected client-side XSS and a persistent client-side XSS. And what is happening now is that I'm just clearing all the storage, such that we have a clear browsing setup, that nothing was tampered beforehand. Now we visit our target website. In this case, it's umeng.com. Also, I don't speak Chinese, so if there's anything offensive on there, my apologies. So this is like the normal website, such that you get a look and a feel. And as typical for a setting of a web attacker, you lure your victim onto some site promising cat videos or cat pictures. And in this case, you can see in the background there's an XSS being exploited. Obviously, this would be hidden in a real attack. And what is important now that I've closed all the browsing windows, so there was no JavaScript being executed. This could, for example, also incorporate a context switch from the coffee shop to your home. And then you are again greeted with a login form. In that case, the attack just pops up in the alert box showing your username and your password. And this again shows the threat, how this can be much more severe than a simple XSS. And to sum up, what you've seen now is a large-scale study about the top 5,000 most important websites according to Alexa. We found evidence that 1,950 make use of storage somewhere in their application, and 1,320 make so without encoding at least once. We've seen that 418 exhibit an exploitable flow, out of which we can exploit around 290 for a network attacker and around 65 for a web attacker. And the thing which I want you to take home with is that persistent client-side XSS is actually a widespread issue and an issue we have to deal with and an issue we have to have our developers understand. And with that, I'd like to close, and I'm happy to take any questions if there are any.
Yes, thank you very much, Marius. And we already have the first one to propose a question.
Yeah. Hello. It's more a remark about the Hsts and the include subdomains. Yeah. That may not even be enough, because if you have a situation where you set your Hsts on www.domain.com, then you may not have loaded the Hsts for the plain domain. So if you don't have preloading and you set your include subdomain on www, you can still set cookies from the plain domain or from other subdomains.
Indeed, yeah. Thank you for the remark. But we did not have a real look into that situation. Yeah. So, yeah.
One more question, yes.
Hi, you spoke about integrity protection and service workers. Is there anything out there that we can use?
So these are like two distinct things which you can make use of. So either you perform some integrity measure yourself in your JavaScript code. So for example, you store jQuery somewhere in the local storage, and you just expect there to be jQuery, so you have a hash of that, for example. Okay. And before you eval it, you check the hash. And on the other hand side, service workers are actually intended to perform some caching mechanisms. So this is like one of the main use cases of these. And yeah, what you can just do is have this caching take place in the scope of the service worker, so it's inaccessible from the site. Yeah. And the service worker intercepts requests to resources and then serves the cached responses. So this is essentially what you can do in a service worker.
Okay, thanks.
Do we have any more questions? Otherwise, we would go to the next talk. We have one more.
So with the rise of like the new web frameworks like Vue, Angular, and stuff like that, do you feel like there is some more baseline of security because people are using these kind of frameworks? And basically the question, how many of these domains who had like really big exploits were using, let's say like some kind of framework to bootstrap their front-end application?
So we did not have a look at how many of the sites which we found exploitable actually made use of some frameworks or stuff like that. What we did found is that lots of these vulnerabilities actually reside in third-party code. So for example, a library which you include, which actually just then exhibits the vulnerability. And we've also reported the vulnerabilities to these library providers. And what we found is that some of these are actually quite responsive and take this threat seriously, but others actually don't. And I think with that, we just need to raise awareness that there is this threat, and that even if either if you make use of like these libraries or not, the developer needs to be aware that there is this threat present in the web. So.
Okay, thank you.
Thank you.
Then thank you very much, Marius.
Thanks.
Please, another.